Welcome to this presentation about mirror and lens systems. We're going to look at two types, converging and diverging. So in our converging lens systems, we have concave mirrors and convex lenses, diverging convex mirrors and concave lenses. Now the thing we're going to look at here is when you take a ray that comes from a distant source and see what happens. And you can see when you have a converging mirror or lens system, the rays reflect or refract actually through a focal point. They physically cross through that focal point. On the other hand, a diverging mirror or lens system, the rays don't pass through the focal point. They bend as if they came from the focal point, but they don't actually pass through it, which means for a converging mirror or lens system, we can say that the focal point is going to be real. The rays actually do bend through it. It's an actual real focal point. On the other hand, diverging, virtual. So to summarize this section, if we have a concave or converging mirror or lens system, the focal point is going to be positive when we do maths. If we're looking at a diverging mirror system, the focal point is going to be negative. So we're looking at an example here with a distant object. Our first ray goes parallel to the principal axis through the focal point. The second one is an equal angle either side of the principal axis, and then you'll see our third one there. You only need to draw two, any two, and then we draw our image where those lines converge, wherever that is. And we can also do that mathematically. We're expecting to get a positive number, and you can see that we do, and you can see there how I've rearranged and then I invert as the last step. On the other hand, when we come to do the heights, it doesn't matter whether something's positive or negative when we do the heights. Let's look at our second example. This time the object is near the mirror, inside the focal point. First ray is the same. Second ray, the equal angles, the same. They can't meet, so we draw the backwards extensions this time. And you'll see the image forms behind the mirror. This time the image is virtual. We're expecting a negative number for our DI, our distance to our image, and you can see there we get an answer of -3. However, when we look at our heights, okay, we're not interested in above or below. We're not going to have minus signs on that. We just work it out. So this is a lens with a distant object, and so what we're expecting to see here, again, the focal point is positive. It's a real focal point, and we set up those two rays, and our third ray we can draw that on too. You only need to draw two rays. So in this case our image is real, and we can show that mathematically. It forms at 6.3 centimeters in the real section of the lens system, and we can work out how big it is. This is with a near object, so it's still a converging lens, but it's a near object. And you can see that our three lines cannot join, so we're looking at the backward extensions again. When we solve that mathematically, you can see that I have dropped a minus sign there. You're not going to make that mistake, are you? So now we're looking at the first of our diverging. So to see the ray comes in and bends as if it comes from that virtual focal point. The equal angle rule still applies exactly the same. However, those rays can't join, so we look at the backward extensions to find the image. And when we solve that mathematically, we're expecting to get a negative number. It's a virtual focal point. We're expecting to get a virtual image. And so if that doesn't say something negative, it should. And our last one with a concave lens, you can see that it's again, this time it's coming from the focal point that's behind the lens. It's diverging. And we use those backward extensions, and you can see where the image forms. When we solve that mathematically, this time remember f is going to be negative, and we put that -5 in there and we find out where it is. And this image is virtual as well,